and then Tom will finish. And then I've added so we'll start the masterclass by covering in software what we did last lecture, which was computing Cauchy transforms over arbitrary contours, and we'll just see that it actually works. Tom, due to popular demand, has added a fourth section, which is rigorous aspects, I guess. So for everybody who doesn't like the notion of nice functions, we have a special fourth section. And then I guess applications, and then finally, probably tomorrow, Cephas ascent for Riemann-Hilbert problems. All right. So before we get to 3, I'll do 1 and 2 in software. So last lecture we saw that Cauchy transforms we outlined in a general approach. Instead of using, so Cauchy transform is integral in the complex. So we looked at the computation of this function. So given a function f on a contour gamma, this generates a function analytic off gamma. And we outlined this approach of if gamma is -1, 1, we can use orthogonal polynomials to calculate the Cauchy transform. If gamma is not -1, 1, we can use change of variable formula specific to the Cauchy transform to calculate it. So let's just see it in software. So here's an arbitrary function, cos 5x, that I've expanded in Legendre series. So these are the Legendre coefficients. And then we can see that this is the Cauchy transform that's essentially accurate to machine precision all the way up to -1, 1 of this arbitrary function. Okay, so essentially we expand in Legendre coefficients. We can calculate the Cauchy transform of Legendre polynomials using the 3-term recurrence, and far away from the interval, we use the backward 2-point boundary value problem. Close to the interval, we use forward recursion. And this is accurate all the way up to the interval, to essentially machine precision. This sort of is an alternative to doing the naive thing of using Gauss-Legendre points and doing the quadrature discretization of the integral, in which case we get, as we saw in Nick's talk, it's very accurate away from the interval, but as we approach the interval, we get poles. Okay, so by using this approach of using orthogonal polynomials, we can actually calculate Cauchy transforms all the way up to the interval. Now, what if it's not -1, 1? What if it's an arbitrary contour, let's say parameterized by this? So here's a plot of a contour that I just made up. It could be something more complicated, but for simplicity, we'll use this. So here's an arbitrary contour. What if we want a Cauchy transform on this contour? Well, we approximate it by a polynomial. We use Chebyshev expansion. So I say this is a parameterization of the contour. I do a Chebyshev approximation. And then this is just sort of a wrapper to say that I want to treat this function as the definition of a contour. Okay? And as we saw last lecture, that we can calculate Cauchy transforms under polynomial maps of -1, 1 using this change of variable formula. So then we can expand a function under maps Legendre and calculate its Cauchy transform. And again, it's accurate all the way up to the up to the contour. So the point is that we can basically calculate Cauchy transforms over any arbitrary piecewise smooth contour and have it be accurate uniformly in the complex plane. Where obviously if I did quadrature, there would be poles along here. Okay. Now this is really relevant for Riemann-Hilbert problems, but I just wanted to mention this is not specific to the Cauchy transform. We can do, for example, the log transform over polynomial maps of -1, 1, or using a similar formula. I didn't write it, but it's very close. So we can calculate the log kernel of, I took the real part of f just to make it real. And we can see here that it matches the integration definition, essentially up to roughly machine precision. And this will also be accurate as we approach gamma. So we can do not just Cauchy kernels, but also log kernels. Well, for the gamma stuff, it's an unpublished paper with Mikhail Slavinsky, who unfortunately was out with me last night, so he's not he's not here. But it's but I'm here. But for the Cauchy transforms, it's in the book with Tom. But it's sort of. The irony is, I was very proud of myself when I got to this, because I was thinking, now I can do past the steepest descent. And I think, as you commented on Don's talk, well, you don't actually need the path of steepest descent, because you can just use an approximation to the path of steepest descent. So it turned out that we don't need any of this for Riemann-Hilbert problems, but it's still a nice idea. Yeah. Right, so originally I actually used Chebyshev polynomials, and then you can write down the Cauchy transform explicitly in terms of hypergeometric functions. Then which are implemented in Mathematica, which is what I use, because originally there was RH package in Mathematica. Then I ported everything to Julia, and at the time there was not a hypergeometric package in Julia. So the advantage of Legendre polynomials is that we can calculate them using a 3-term recurrence rather than explicit representations as hypergeometric functions. So if you remember last lecture, so at least away from the interval, we use the fact that the Cauchy transform of Legendre satisfies the 3-term recurrence. So J is the Jacobi operator for Legendre polynomials. So if Z is away from -1, 1, we can just solve this. It's an invertible equation. We can use finite section, or we can use these adaptive approaches, SWJ Olver's algorithm, for example, and calculate all the Cauchy transforms of Legendre polynomials. And then when Z is close to -1, 1, we use forward recurrence. So it's sort of like a technical aspect that you don't need special functions here.
One more question. When the density function does not vanish at the end of the contour, because the transform is unbounded to the endpoint. So does this mean anything?
Yeah, well, that's actually, I was hoping to gloss over it, but yeah, so it behaves like log at the endpoints. And that actually is an important point when we get to actually when we're talking about collocation with Riemann-Hilbert problems. So, as I mentioned briefly last lecture, the Cauchy transform of 1 of Z is log of Z minus 1 minus log of Z plus 1 over 2 pi I. It has weaker than pole singularities, but it does have singularities at -1, 1. And this is important. So here, I don't know why you don't see it, but apparently there's log singularities here, because I'm expanding a smooth function. Okay. but the point is we can do Cauchy transforms on quite complicated contours and have it be accurate up to machine precision all the way. We can evaluate on the contour. That's actually not that hard, because you can always subtract the singularity and add it back in again, but also arbitrarily close, which is which is quite nice. All right. So what does this have to do with Riemann-Hilbert problems? So Riemann-Hilbert problems, if we remember, consists of, okay, we specify a contour gamma. These can be complicated contours, but let's focus on the Hastings-MacLeod solution. So if you remember, we have a 2x2 Riemann-Hilbert problem on a contour like this, and the whole idea behind the collocation method is we write. So we want phi of z. So S is a point on the contour. We're given G. Let's assume f is 0. We want to solve phi plus S is equal to, and it's going to make things simpler if it's GS phi minus of S. So we want to find an analytic function, phi of Z, analytic off the contour. In this case, it's a piecewise sectional analytic function that satisfies the prescribed jump on the branch cuts on gamma. All right. And then there's sort of a basic, almost representation theory fact that if you want an analytic function off a contour, we can write it as a Cauchy transform of a function on the contour. So we write phi of z is equal to, well, if you remember from Riemann-Hilbert problems, we wanted to go to identity plus infinity plus something that vanishes. And then this is sort of, we don't know what v is. Okay. Now plugging this in, 2 phi plus equals g of s, or more generally, phi plus minus g, phi minus is equal to f. We're given g, we're given f, find phi. We get a singular integral equation. So we get I plus c plus v minus g times I plus c minus v is equal to f, which is equivalent to c plus v minus g times c minus v is equal to f plus I minus g. Have I done this right? Yeah. Yes, that's what I thought. Okay. Plus g minus I. Okay. Oh, yeah, because you put, it's a minus sign when you move things from the left to the right. Yeah. Thanks, Tom. Okay. And now, for whatever reason, functional analysis analysts like to write things as identity plus something else. I don't know why. Maybe someone in the audience will inform me why it's important. But this is equivalent to V, or I identity plus, so we can use a property that C plus minus C minus is equal to identity to recast this as I plus G minus I, C minus V is equal to F plus G minus I, and call this F tilde. Okay, so a Riemann-Hilbert problem really is a singular integral equation, which is identity plus some function times C minus. And I said I don't know why people like to write it as identity plus something, but this is actually quite nice because it at least tells us that if G is close to the identity, and then we can use norms on the Cauchy transform to say that it's identity plus something small norm. So at least if G is close to the identity, we can say this is a well-posed singular integral equation, though it's relevant for even G far from the identity. Okay, but basically, if we can calculate V, we know phi, and we know how to calculate phi arbitrarily in the complex plane. So the problem really is, how do we solve the singular integral equation to calculate V? And this is over some complicated contour like gamma. Well, as I sort of alluded to, we're going to solve this singular integral equation using collocation. And the point is, if we use our basis built out of mapped orthogonal polynomials, we can at least apply the Cauchy transform C minus times the basis explicitly. So we don't even need any numerical approximation of the Cauchy transform. We can just calculate it explicitly. So it's basically, so part 3 is solve it with collocation, and we're done. But maybe it's worth saying a bit more. So we have gamma, which is composed of a bunch of pieces. We map each one to minus 1, 1. So let's say here's just an affine map, but as we saw in code, it can be sort of a more general map. So we map either using Mobius transformations, rational approximations, polynomial transformations, minus 1, 1 to our sequence of contours. So we have, say, in this case, we have 4 maps. We represent the solution V that we want to find on the contour gamma as I'll write 4, but 4 obviously means the number of contours, because we can have an arbitrarily complicated.
So you have 4 different maps.
Yeah.
But then already yesterday in Trogdon mentioned about the problem. You probably shift on the contour, no?
What?
You have different maps for each quadrant. Then you probably
No, I'm not mapping the quadrants. I'm mapping the contour. These are maps from minus 1, 1 to contour, as long as M is either polynomial or rational, or as long as M is rational, we know how to relate the Cauchy transform over the map contour to Cauchy transforms on minus 1.
This change of variables.
Yeah, the change of variables that I mentioned, which is different from integral change of variables. So now we represent our unknown, V, which is defined on each of these 4 contours in terms of the map basis. So we can think of it as summing over the contours, sum over k equals 0 to, maybe I want to say we approximate V by sum up to n. And for the purposes of this talk, and also for the purposes of having an implementation in RiemannHilbert.jl, we assume that the number of coefficients in each contour is the same. This is obviously not necessary. We can use different things, but these are the expansion coefficients, and then we use the basis Legendre polynomials of so this is just saying that we use a piecewise. We map Legendre polynomials to whatever our contours are and do a piecewise approximation. What's that? Yeah. It has a singularity here. That's an important point. So let's call this whole thing L. So we want to solve LV is equal to F tilde. Well, the thing is, with this basis, we can apply L to the basis, L to map Legendre polynomials, use the change of variable formulas to relate it to Cauchy transforms of -1, 1. And so actually we can apply L to the basis and evaluate it exactly. So in terms of collocation, we just want to put down a sequence of points S1. So we lay down a grid on our sequence of contours, and we want, what we're going to do is impose this equation point-wise. So we're going to choose these coefficients by solving the linear system. These are our unknowns. Let's call this whole thing psi k. This is our basis, our piecewise mapped Legendre polynomials. Okay. And if we choose the number of points, the number of collocation points, equal to the number of unknowns, we get a square discretization. And the important point is we know this exactly. Everywhere in the complex plane. Yep. Yeah, actually, that's what we do. So, as people in the audience are alluding to, there's a problem. This is actually why I wrote this Cauchy transform, to highlight that the problem is the Cauchy transform of Legendre polynomials on -1, 1 actually has singularities. So there's a problem, is that if we do this and we don't think carefully, the Cauchy transform on each of these map contours will blow up at the origin, or actually at the endpoint. In practice, not because we need to, we can use conformal maps to infinite rays. In practice, it's faster to use affine transformations. So we map to this thing with unbounded contours is actually numerically approximated by something with bounded contours. You would have blow up here. Well, the blow up here is actually not that big a deal because things are exponentially decaying to the identity. So we have g minus I is actually equal to 0. So in the collocation system, for all intents and purposes, g minus I is 0 at the open endpoints. We actually don't, it's not a problem. But here, well, we have things like what I wrote last lecture, 1, 1, either plus or minus I. I think it's plus e to the I s cubed. As s goes to 0, this does not approach identity. So actually, the issue is not the open endpoint. So the issue is this junction point. So what's the solution? What we actually do is we add collocation points at the origin, but one on each ray. So our SJs include sort of an epsilon perturbation from the origin on each ray. So we have collocation points at 0. We have 4 collocations at 0 plus epsilon times e to the I, in this case, pi over 6, was it? I don't remember. But well, no. So we want collocation points, one corresponding to each of these. But the problem with this is then we plug it into this formula. So you plug in 0. Well, if we plugged in just 0, we get L of psi kj of 0, which is mapped to minus 1, 1. So we get L of, for example, 1 of 1. And then you see, for example, even just the first basis function blows up. So if we did this naively and just put in 0, we would get this is equal to infinity. OK, so how do we get around this? Well, there's this very nice concept of how many people here know automatic differentiation? Quite a few. Well, everyone, if you ever want to talk about machine learning is almost 100% automatic differentiation. But that's speaking as someone who knows nothing about machine learning. But essentially, we can think of this as a special type, say a dual number, of a point plus an infinitesimally small perturbation. So back to minus 1, 1, because everything ends up being mapped to minus 1, 1. The question really comes down to how do we make sense of Cauchy transform of, let's keep things simple, 1 of applied to a dual number Okay. Well, if we're allowed to, if we're allowing ourselves to have epsilon perturbations, then we can make sense of this by, so the issue is you have 1 plus epsilon, you have log of 0, infinity plus epsilon. Well, if we're allowing ourselves to create something called a dual number, let's also create something called a log number. So this is actually epsilon is real and infinitesimal small. Log of epsilon times e to the I theta is one plus one. What's one plus one? I think even I can do that one. Or more simply, we have a log epsilon plus b. And here I'm at this point I'm less concerned with mathematics just in terms of software implementation, but they're closely related. we can have a special type for dual numbers, and in Julia this is implemented, and evaluate Cauchy transform at a dual number at where it blows up, and represent it by a different special type as a log epsilon plus b. And the beauty of Riemann-Hilbert problems is, so it's sort of time to let Tom take over, so I'm not going to go into details. But so we have a collocation system. What? Okay. That we're imposing these conditions at these dual numbers on each ray. Each one blows up. And the beauty is that if we just ignore the log term, we get a well-posed linear system, because it turns out V itself satisfies a special condition called the zero-sum condition, which I guess Tom will talk about, that ensures that we know the solutions don't blow up. We know the solution doesn't blow up. We know these log terms eventually disappear. It turns out in the collocation system we can just ignore this part in collocation and take this as what I think we call it the finite part Cauchy transform. Okay. Does that answer your question? And it was sort of by chance that I just ignored that, put it into the collocation system, it all worked out. Okay, so the point is we can solve Riemann-Hilbert problems numerically. We can find these coefficients v, k, j by solving this collocation system. This is evaluatable exactly on Sj away from the endpoints. So that's not a problem. At the endpoints, we ignore the logarithmic blow up and just take that as a definition of L psi k. That gives us an n by n matrix with no infinities in it, so something we can solve. Turns out it's well conditioned, very well conditioned, and therefore we can find these unknown coefficients, which tells us a very good approximation to V. It's essentially a spectral method, so we get spectral accuracy. We find V defined on gamma, and then we can evaluate the solution anywhere in the complex plane by writing it as I plus Cauchy transform. All right. Okay. So while we swap laptops, any questions? Yep. What we're doing right now. This is one of what. Sorry, I wrote it only for one. Actually, we use the feature of the current to actually calculate Cauchy transform of the Gaussian polynomial, but it's exactly the same thing. In fact, the Cauchy transform of F is f times log. Well, f over 2 pi I times log. So here, in this case, f is 1. We have 1 over 2 pi I times log f. One is not one, one is out. We have Cauchy transform of F is F evaluated as 0. So why don't we? Well, we don't because we do.
I think I'll explain some.
What? Was not known to you.
I'll try unplugging and plugging back.
I
nice thing about factual methods is you essentially have error controls. You look at the large degree coefficients if they're below a tolerance. And the general property of collocation is we don't actually have proof of convergence, but if we had control on the condition number of this relation, that encodes
you take other than matrices, you just swap experiments will still be there, but because you have nice Trogdon structure, they will cancel each other.
Yeah, exactly. So B has a property that they C on the interval sums to 0.
It's all minus on certain
It's all in this next slides. It's all here. I will explain. Yes. Okay. So I'm going to originally applications. I'm going to bow to Sheehan's outline and probably finish up with the theory today, and then tomorrow give you some applications and talk about oscillatory problems. Okay. So to really kind of set up a Riemann-Hilbert problem correctly, you have to go into the theory of Hardy spaces, or this is really one way, right? And so Sheehan has that we represent the solution at the top, phi, as the identity plus the Cauchy integral of something. And you have to justify that. And you have to justify that when you set up your Riemann-Hilbert problem, right? That's an ansatz. You can see that it works in practice, but what's the real justification for that? And right, so there's the Hardy spaces. The easiest one to define is, say, the Hardy space of the upper half plane, or inside maybe in the unit circle, where you have a certain L2 estimate uniformly along horizontal strips or horizontal lines in the upper half plane. Okay, and so you look at all functions, analytic, upper half plane, such that that integral, the sup over R, is finite. Okay, and I'm going to go with Nick's scheme and overwhelm you with as much as I can. Right, so if you really want to do this in the full generality, you have to use what are called Carlson curves. So this applies to general, not truly smooth curves, but this is actually a very useful thing in practice, right? So you can take some finite union of curves that are all some bounded variation mapping of intervals, take their union, and then you look at the arc length inside balls, and you can do an estimate, and as long as this is finite, you have a Carlson curve. Okay, so why would we want to use this? Well, the operator norm of these Cauchy operators depends continuously on this. So you have a problem where you have some complicated array of contours. It really lets you look at it and say, okay, this is my operator norm is bounded by a certain value, even if everything's piecewise affine, nicely smooth. Okay. And so then you can use all of this machinery and generalize, the whole Plumel lemma that Sheehan talked about to general contours, non-smooth function spaces, and so on. Right? So the top line is Plumel on these Carlson curves. For us, it's going to end up being piecewise smooth curves, right? Piecewise linear, really. You have projection properties. C plus times C plus is C plus. And you also have these nice properties if your contours are set up in the right way, so you can color one region. So you can color regions white and black, and no black region borders on a black region. Okay. And then you can say, actually, the Cauchy integral of L2 on this curve is the entire Hardy space. So now there's a one-to-one correspondence between functions analytic off and analytic on. Okay. Right, and this is the definiteness that Sheehan talked about, right? So if C plus minus C minus is 0, then the function itself must be 0. Okay, so this is then how you set up a Riemann-Hilbert problem where you can justify that ansatz at the top. Okay, so right, so we look for this Hardy space solution of this phi plus equals phi minus, and we call it if phi minus I is in the Hardy space, which is to say that phi has a representation as identity plus the Cauchy integral of something. Okay? And there's, you have these estimates, so you can, when you pose a Riemann-Hilbert problem, do estimates as you're setting things up to prove that, yes, this is a well-posed Hardy space Riemann-Hilbert problem. Right? And then this is just the calculation right here that Sheehan did there. Right? So you take your Riemann-Hilbert problem, and you end up with a singular integral operator with g minus I on the right-hand side. Okay, so spectral convergence. We had questions about spectral convergence. How do you understand this, right? So we have to understand smoothness of solutions from a couple perspectives. One, we want to understand if the solution is differentiable, how many times, and we want to understand how derivatives grow with parameters, because once we get to some of the applications, there will be an external parameter in the problem, and as you change that external parameter for the Riemann-Hilbert problem, how do derivatives change? And if derivatives are blowing up, solutions, your convergence rate will be diminished. Okay? And so, right, so we're worried about singularities at this intersection point. We're worried about what can happen here, right? And so this is kind of maybe a complicated way of stating things, but basically, if you have function values and derivatives matching at the right way at that intersection point, all of your logarithmic terms cancel out to the right order, right? So so just think about all rays being oriented outward. So if the sum of the limits of my function values is 0, I won't have a logarithmic singularity to first order. And if my derivatives satisfy the second one, I won't have a logarithmic singularity to second order, right? Okay, so you originally defined these, HK Sobolev spaces on each contour, and then you can't have contours be independent because you need some sort of behavior at intersection points. Yes? That's right. That's right. So if you have this, so at a free endpoint, this condition amounts to functions that vanish at that endpoint. Okay. And so you can then look at this Sobolev space. This has the zero-sum condition built in. Right? So now you have all of your contours, Sobolev spaces, and you have this zero-sum condition that happens at every single intersection point on the contour. Once you have that, now the Cauchy operator maps that space to itself. It preserves the smoothness of those of those functions. Okay. Right. So we now know that if we have a function defined on this contour that matches in the right way here, I take the Cauchy transform, I take its limit back to the contour, I get another function that satisfies the same property, the same condition. So I can now repeatedly apply the Cauchy operator if I like. Okay, so that's a nice space of functions for the Cauchy operator to work on. What happens so that the Riemann-Hilbert problem could potentially have a solution in that space, right? And this is what you were, I think, just alluding to, that there is a condition. So if we have this, let's ignore F for a second. Let's just have G. There's a condition that G must satisfy at every single self-intersection point. And instead of it being a sum condition, it's basically saying that as I march around jumping across every contour, I should get back to the identity matrix. I should not branch as I jump around all the contours. And you can generalize that to higher order. Right. I mean, so but then F, you have to worry a little bit about what properties F has. F should satisfy the zero-sum condition. Okay. Right. Okay. Yes. It's not, but you can often deform the problem so that it is. So when I'll go through an example involving the area function where all of this stuff is violated, and we'll work through changing the problem into one where all of our conditions are satisfied. Okay, and so if you like your indices, you can compute the Fredholm index and in most cases, like the determinant of the jump matrix, most applications is 1. Right? So you have Fredholm index 0, and then you have to work on showing that the kernel is trivial. Okay. And so I like this because there's this kind of operator script M up there. And it's the existence of this operator. You can use these works to show. But we never need it, right? Because we'll just solve, if it was the script, if it was the singular integral operator composed with M the other way, I would kind of need M to figure out what the solution is. But it turns out the way it's posed, we just never even need M in practice. Okay, and so for convergence, we have to understand derivatives of solutions. Right? And so it's really not so hard. You just take your singular integral equation right there, and you just differentiate it. You differentiate it, you eventually have the singular integral operator on the left times the kth derivative of v. You invert that operator, put it to the right, and estimate things. And so you can really just estimate the solution in terms of derivatives of your jump matrix, the operator itself, and the main thing is, in all of this, to really understand what's going on, we're going to have to understand the inverse, the norm of the inverse, and that's the hardest part. Right? We can calculate with the jump matrix, get all explicit estimates there. The Carlson constant is easy. That will show up in the norm of the operator. But this is where, in the next lecture, we'll have to work with steepest descent to try to understand what to do for large values of parameters. Okay. Right, and so this is kind of the consistency check for the numerical method. Right? So Sheehan described how to go from a singular integral operator to a Chebyshev discretization, which I'll call C sub n. Right, and okay, this does not require Chebyshev collocation. It just requires collocation. Right, it's technically Legendre, right? Yeah, so I think it would be true of any collocation where you drop this log term. Right, so if G satisfies this product condition, you set up your collocation system and you solve for UN. Then UN must satisfy the first order zero-sum condition. Right. So this is not obvious. Right. And so what it's actually saying is that throwing away these log terms, enforcing everything at the junction point, is the right way to impose that your solution satisfies the right conditions so that this will now be a bounded function in the complex plane. Right? It won't have a first order singularity. It should just require the product condition, right? Yeah. Okay, and so so when we first put all this together, right, so Sheehan developed this Riemann-Hilbert package in Mathematica, and then we stuck on top of it an inverse scattering package for integrable PDEs. And so this has now kind of been replaced by RiemannHilbert.jl, which Sheehan's been talking about, and then over the course of some future years, we'll begin to replace the inverse scattering stuff. Okay, and you see that we have some of it done so far. Okay, and so maybe I will end with a demo. One of my favorite, that's good. So computing the complementary error function. Right? And so we're going to do this using Riemann-Hilbert language. This doesn't require the full machinery of arbitrary contours. The contour is very simple, but it illustrates the ideas, I think. Okay, let's run that. Right, and so this is really based on just a reinterpretation of something that Andre did. Okay, and so the goal is to compute the complementary error function in the entire complex plane and rephrase the integral for the error function here, change it around so that we can phrase it as a Riemann-Hilbert problem. Okay? So right now we could look at I won't say that. Okay, so here's our complementary error function, and what you can do is you can do different transformations of it in the right and left half plane. Right? So for real z positive, it decays rapidly, so I'll do an integration by parts, figure out its leading order behavior, and deal with that. And then, okay, as for real z negative, it tends to 2, so we subtract 2 basically, and then figure out its decay rate and multiply by that. Okay, so now phi, I have 2 different definitions, left, right-hand planes. So it will now have a jump on the imaginary axis. Right? It's in each piece has obviously an analytic continuation to the whole complex plane, but sectionally defined, it has a jump on the imaginary axis. Okay. More than that, though, if you do integration by parts, you'll see that these functions in the top and the bottom go as 1 over z as z goes to infinity. Right? And you can do then the Hardy space estimates very easily and see that, yes, this phi in the right half plane is a Hardy space function, phi in the left is a Hardy space function. You don't really need that, but it's kind of a nice way to check all the theory. Okay? And then you go and you compute, let me get the stick. Right? And you go and you compute the jump. Right? And so we're on the imaginary axis, so this is an extremely nice function on the imaginary axis. Right? Okay? Right? So then we don't need a collocation, right? Because we have phi plus minus phi minus. How do I compute phi? Phi is just the Cauchy integral of this. Right? So I just need to compute the Cauchy integral along the imaginary axis of this, effectively a Gaussian. Okay, and so in this approx fun Fourier, you can easily expand a function in a rational basis. Right? And you have this extra parameter L hiding in here, so it makes sense to optimize L to use the fewest number of basis functions. Okay, so what I'm going to do is take the 2e to the z squared, expand it in a rational basis, optimize over L to find the best choice. Right? And that's easy to do, so let me first just print out what L is. Right, so there we go. L, so that was some compile time. Yeah, much faster the second time. Right, so we find, this is a rough estimate, right? Find L is about 2.4. And okay, we could check then right, so let's check the length. Right, and so this is, so we need 109 coefficients in the rational expansion, and the way this is done, as I construct the fun in approx fun, it's done adaptively. Right, so now I know that this is basically the optimal choice of L to get machine accuracy and I end up with 109 coefficients.
Why don't I recall that it's much less than that? For the PDE places.
Right, so were you using the Malmquist, the basis that...
Isn't it the same?
So maybe it could be the way in which the adaptivity works. Right. Right. Let's check that. Yeah, so it's taking too many. Right. Okay. And so then you can use the singular integral equations package by Mikkel and Sheehan. Allows us to then compute the coefficient. So here is now with my choice of L, I have my fun, which is my Gaussian along the imaginary axis. And then here's just the piecewise unwinding of what I've done. Right. So now I have my error function and computing it. Okay, this is just that x is -1, giving me machine accuracy. Right, and we can kind of, right, I guess, let me think about, we can play around with different values. Let's see how we do. That's not good. But, I mean, error function, so I'm looking at the, right, I was looking at, it's exponentially growing or decaying, and I was looking at a relative error. So things are going to be bad. Okay? So this kind of gives you a flavor of how the Riemann-Hilbert machinery lends itself to a special function. So next time I will start with working with the Airy function, doing roughly the same thing, but shows the more complicated deformations and kind of conditioning of the problem that you have to do. Okay? So I guess I'll stop there. No. So typically what we have is a jump matrix. So we have these infinite contours, and the jump matrix tends to identity at infinity. So in practice, you can truncate that at some point, but then the jump matrix is to machine precision the identity. And so you effectively don't have a free endpoint in a sense. Because you still satisfy the product condition, and then the solution will satisfy the zero-sum condition. So the solution will vanish at that point.
About your last example, basically your last applications are related to integral, the integral from 0 to infinity. This I would say, very strongly exponentially minus x squared.
Right.
But there are also formulas, high algebraic precision, for exponential became functional as integral using Olver polynomials.
So you're suggesting using... Well, in this case, I mean, we're actually, in a sense, we're taking the whole imaginary axis and mapping it to the unit circle using the periodicity expanding in a rational basis and then computing the Cauchy integral exactly once you have that. Right. Yeah, and then that should give you higher decay as you leave the contour. Yeah. Right. Yeah, yeah, and then as you've seen from Sheehan's talk, then those will satisfy, the Cauchy integrals of those will satisfy a 3-term recurrence, and you could compute them all that way.